Okay, so this is part 3 of homework 1. I will read really quick from Canvas what we need to be doing for this part, and then I will be working through my iPad, and then we will go back into Collaboratory like we did for the rest of the parts. So, part C. A proportional controller is used to control the liquid level in the third tank by adjusting the flow into the first tank. Derive the differential equations describing the controlled response for different proportional gain values. Simulate the response of the system to a 10% set point increase in the liquid level of the third tank. So, going to my iPad, we have the same scenario as part B with the 3 tanks. However, we want to control the liquid height in tank 3 by adjusting the flow rate coming into tank 1 using a proportional controller. So, kind of looking at what a PID controller looks like, we need an expression for the new Qn. This is going to be equal to some proportional constant. This is the controller gain. We're going to shoot for, we need a set point for the height in tank 3. So we'll call that height 3 set point, and this is subtracted from height 3. And this kind of looks at the difference in like the deviations from where the heights can need to be based on how we're changing the flow rate coming into tank 1. And then this proportional controller KC will be adjusted based off of, that, sorry, my bad. And then this also, we're adding the initial flow rate as well. So we can call this part, this is the error, the deviation from the set point, we'll call that E. And then another part of the PID controller is the integral and derivative portion of that. So if we include that, it'll look something like this. So the initial flow rate coming in plus this proportional constant multiplied by this error. However, we need to add this differential part, 1 over tau I. Tau I is the set point where the integral will be restarting, and then the integral part of this is just E dt prime. So this is controlling the flow rate coming in as a like direct proportional change, as well as this differential adjustments as well, which will control the oscillations so that the steady state will be reached more efficiently. So we can call this portion the error integral, and then we're going to need an initial guess. So say the error integral naught will be 0. So now that we have these expressions, we can go into Collaboratory and incorporate this into what we had for part B. So we can include this controller to control the liquid height in tank 3 by changing Q in. And we want, or the set point for the third height is just what we had, our expression for H naught multiplied by 1.1 because we're increasing by 10%. So let's hop over to Collaboratory. So now that we're in Collaboratory, this is the same code that I had from part B. We need to initialize some of the additional parameters that we have. Our first is going to be the height 3 set point. That is just H naught multiplied by 1.1 because we're increasing by 10%. Our error int naught, our initial guess for the error integral, is going to be set to 0. Our tau I, we'll set that to, let's just say 500. That's our int set point. We need kind of an initial guess for KC at what as to what we're starting with. I'll begin at 0.01. And then I believe that is everything that we need here. So now to adjust our function here, we need to include error_int as to part of this vector. We need to define what our error sort of is. So that's just the difference between the third tank level height set point subtracted from the actual set point. And then we need to modify this expression for Qn. It is no longer just multiplied by this increase factor of 20%. So this is going to look like something like this, where the initial flow rate coming in is going to be equal to the proportionality constant multiplied by the error plus the error integral divided by the set point tau I. And then as well, we want to return this, we want to return the error. So now that we have that, and then we need to adjust this as well. We need to include the initial guess for our error integral, which we, in this case, chose to be 0. And then as well for the y-axis component, after we use the solve initial value problem, the ODE solver, we need to include the error_int here as well. So let's take a look at what this looks like. So as you can see, there's slight oscillation and then it reaches that steady state here. Let me adjust so I can reset. So as you can see, it does fluctuate and then it does reach that steady state. So let's take a look at what that would look like if we didn't include the error integral piece. So that would just be Qn plus this proportionality constant multiplied by our error. So just K times E. So we could completely let's see how this is going to look. Yeah, it's a little similar, but just the only difference is that the integral derivative portion of the PID controller is to minimize the oscillations that occur, so that we reach that target set point more efficiently. And yeah, so that's basically everything for part 3 for homework 1. Thank you.